Faraday's Law. In this lab, we analyzed the motion of a magnet falling through an aluminum foil tube. We related a time-varying magnetic field to a Curry electric field. The electric field provides a current which exerts a force on the magnet. This caused the magnet to go much slower than expected. We would expect the magnet to fall a distance of 0.305 meters in approximately 0.2 seconds. But what we measured was approximately 1.6 seconds on average. The first step of this lab was to find the north and south poles on a bar magnet using a magnetometer app on a smartphone. This was done by moving the magnet closer and farther from the magnetometer. As R decreased, if the X value of the magnetometer became more negative, we knew the south pole was facing the phone. If the X became more positive, we knew the north pole was facing the phone and this side was marked. Then, we dropped the magnet through a tube of aluminum foil and made sure the north pole was facing down. We repeated this for a total of 5 trials and took the average time. We then created a code model of this experiment and compared the results. In this lab, we used Faraday's law to relate magnetic and electric fields. The source of the external magnetic field in this particular model was the falling bar magnet. This magnet provided an EMF and a current. A current was also induced within the tube of aluminum foil, and the magnetic force was opposing gravitational force and causing the magnet to fall slower than if it were out in open air. The mass of the magnet was approximately 0.021 kilograms, and the length of the tube was found to be 30.5 centimeters. The time we expected the magnet to take was approximately 0.2 seconds. However, as you can see from the data table to the left, the average time across all 5 trials was 1.618 seconds, much longer than initially expected. In the top photo of the code, several constants were established. Then, on the right screenshot, the measurements of the aluminum foil tube were recorded and initial parameters were set to 0. The bottom screenshot is where the aluminum foil tube was created, and this code model represented the aluminum foil tube as a stack of rings. The top code screenshot shows where both the magnetic field equation of a bar magnet and the equation for magnetic flux were created. Then, in the bottom screenshot, after every loop was run, the net force on the magnet was found by adding the magnetic force and the gravitational force, and then changing the position of the bar magnet based on this value. This slide shows the results of my code. The bar magnet is represented in this model as the red and blue colors falling through the tube. On the right-hand side, you can see the graph of the velocity of the bar magnet versus the time. And this particular model found that the magnet took approximately 3.39 seconds to fall through the tube. In this code representation, using the right-hand rule, you can find that the blue color corresponds to a clockwise current because the magnitude of the current increases down. Alternatively, the red color rings correspond to a counterclockwise current because the magnitude of the current increases upwards, shown by the intensity of the color. The total time in the computational model is 3.39 seconds, but the real-world time was about 1.6 seconds. This could be made more accurate by adjusting the rate of the magnet's fall or the internal clock of the GlowScript program. Initially, gravity was the only force accelerating the magnet downwards, but as soon as the magnet started moving within the tube, a magnetic force was experienced in the upwards direction and slowed the magnet down substantially. Aluminum is a non-ferrous metal and is therefore not magnetic. If we had used a ferrous tube for this lab, it would be magnetic, and the magnet would just stick to the tube and not fall through it at all. If the resistivity of the conductor was reduced, according to the equation V equals IR, current would increase. If current increases, magnetic field and magnetic force would increase as well, and even completely balance out the gravitational force, causing the magnet to fall much more slowly. If holes were cut in the tube, resistance would increase, current would decrease, according to V equals IR, magnetic field and force would then decrease and the magnet would fall faster.